Okay, so on Friday we looked into where is that? Yeah, this is one. And we looked into k-means clustering. How it does? It chooses a random, it assigns random cluster number to each of the data point, and then takes an average of all those data points and takes that average as the cluster centroid and tries to calculate the distance between that centroid and all the data points, and groups the data which is close to that cluster as one cluster, and groups the second cluster's centroids closest data points as another cluster, third cluster centroid data points as closest data points as another cluster, and again it calculates the mean of all those data points within a cluster, and then again does the same thing, right? So it tries to find out the closest data points to the mean of all those, you know all those data points, and tries to group that as a centroid. You have seen how exactly it is actually moving around, right? And then there should be a goal, right? There must be an optimization objective. We call it as optimization objective. The cost function is called as optimization objective, right? There must be an optimization objective on which on that basis the algorithm actually moves, right? That is this one. Within cluster sum of squares is the WCSS is the objective. So it should, the algorithm will try to reduce this within cluster sum of squares. What is it doing? Within cluster variance across all the clusters it is trying to calculate. What is within cluster variance? From data point to centroid, the Euclidean distance. That Euclidean distance between each data point and centroid, it is summing up throughout all the data points within a cluster, and then summing up within all the clusters. Okay, for each cluster it calculated the Euclidean distance between the data point and the centroid, and then took all the clusters and summed it up, and found out the total score. So initially it's going to be high, as and when we are calculating the centroid and trying to find closest data points and assign it to a cluster, closest data points and assign it to a cluster, closest data point and assign it to cluster, this will reduce, right? In each cluster this number, this metric will reduce. Overall it will reduce. So the algorithm will try to reduce that. So that is what this elbow curve is. So within cluster sum of squares we have taken on y-axis, and as and when we are increasing number of clusters, right, it is reducing. No, there are 2 points. Basically, with cluster number 2, it will try to reduce this and find out a place where it is minimal. Okay, that is this point. Okay, with cluster number 3, it will move around, right? The move around these centroids and groupings, and again try to find the minimal score WCSS. That is this point. And for 5 also, it will actually try to do the same thing, right? It will try to do the clustering and try to find out the groups, 5 groups where each group data point is close to the centroid, and that is this point, right? That is this score, minimal score when the clusters are 5, minimal score when minimal WCSS when clusters are 3, minimal WCSS when the clusters are 2, like that. These are all minimal scores we have actually taken, and then that is the that is the cluster, final cluster, ultimate cluster we are going to do, clustering we are going to do. So we applied that and we reduced, and we actually tried to find the elbow curve. So I see that there is a steep difference, steep change in the error. Till here it was something, but from here onwards, right, the error was not reducing that much. Okay, so if you define each data point as a cluster, as individual cluster, you will get 0 WCSS, but that's not the goal. Where exactly the error reduction is not drastically changing, that point you need to change, that point you need to take. Beyond 3 clusters, even if you do more clusters, the error reduction is not going to be that much. The WCSS is not going to be that much. That means even if you do the more clusters, right, more groups, the grouping may not be that useful beyond this point. Okay, that's the elbow curve's meaning. Okay, there is another way to calculate or look at the error. The error or find out the best cluster. That is called as Shilhau T, right? But they call it a Shilote score. No, you try to take this and put it in Google and try to look at the spelling, right? It it sounds a little weird, but I say Shilote score, right? You just try to. This is English, right? You can do it. You can spell it the way you want. I'm not going to comment on that. Okay. Silhouette analysis is based on. This is a little intelligent way to see whether the clustering happened properly or not. Okay. This is metric actually, right? So for regression we have seen different metrics. For classification we have seen different metrics. For dimensionality reduction we have seen different metric. For dimensionality reduction, the metric we have seen were two, right? If you remember well, one is reconstruction error. Do you remember reconstruction error, right? We were actually trying to uh, reduce the dimensionality and again reconstruct to the original dimensionality and then look at the difference between the original data and the reconstructed data. That is reconstruction error. Or we are actually trying to take that dimensionality reduced data and put it into a model, the supervised model, and see whether the accuracy is the same way or not. So those are the two approaches. For clustering, this is an unsupervised technique, and for clustering, elbow curve and silhouette analysis are the two approaches to two metrics to see whether the model, the clustered grouping is correct or not. Okay, so here silhouette analysis is based on silhouette score. Okay, of a sample, right, between a sample and a neighboring cluster, right, neighboring cluster, a sample and a neighboring cluster. What that means? The score, silhouette score, will show the distance between a sample. I think I need to highlight that, and a neighboring cluster. Let me try to take that and I'll highlight that. I'll forget rather. Give me 1 second. So this is a very intelligent way to check whether two clusters are close or far, or whether the clustering happened properly or not. So where is that? I'll show today, right, how to use clustering to do some image processing also. Right? Let me try to highlight that. A sample and a neighboring cluster. So +1, too far from the neighboring cluster. 0 means on the edge of the neighboring cluster. -1 means too close or overlapping with the neighboring cluster. What these things, I'll explain in a moment. If you look at this, I think this is better. If you look at this, this is one cluster, this is another cluster. Okay. So silhouette score, right? I said that it will show the distance between a sample and a neighboring cluster. I said, right? A sample and a neighboring cluster. I took this sample and trying to calculate distance between all the neighbors in the all the data points in the neighboring cluster. Here in this example, we have only two clusters. If you have three clusters, right, this will take this data point and look at the distances between all the data points in this cluster and that cluster also. If you have 10 clusters, it will actually take this data point and look at the distances between this data point and all the other 9 neighboring clusters. Okay, so the silhouette score is calculated in a different way. There is a formula to calculate that. So if you look at this right, so all these red whatever, right, it is between this data point and the other neighboring cluster. Okay, other neighboring cluster. See this here. What is x1? X1 is around 380, right? 380, 360, whatever, right? And y is also 310, around that. And if you look at the green data points, right, The X is around 260 and 300, right? 260 and 300, right? And then Y is around 370 and 410, 370 and 410, 380 and 410, right? So these are all green data points. These are all red data points. I am actually showing you the distance between this data point and all the data points within the cluster, this data point and all the data points in the neighboring cluster. If you have 10 neighbors, 9 neighbors, right, you'll have 9 blocks like these. It will calculate these scores and keep them aside and then use those scores and put it into this formula. We'll see the formula in a minute. Did you understood the basic idea of silhouette score? Did you get what here we are doing?
In the table, what is that x1 and x2, sir?
There are 2 data points, right? One dot means 2 data points. It's a vector. Each dot is a vector.
Okay.
Right? Here it is a 2-dimensional one because that's where we got 2 data points. If it is 3-dimensional one, we'll get 3 data points. 10-dimensional, 10 data points we'll get. 10, x1, x2, and so on, xn, x10. And I grouped it as this is cluster 0 and this is cluster 1. I named it as 1 and 2. Color coding I gave. Along with that, I gave numbers also. And then I calculate the distance from this data point to the distance. This data point to this data point is this one. Right? This data point to one of these is this one. Right? All these data points. This distance from this data point to all the other data points I calculate. Okay, that is silhouette score. Okay, this score. Right? Now, how exactly the total, the analysis is done, right? We'll see that theoretically. The average silhouette score of all samples explain separation distance between clusters. The average score of all sample silhouette scores. So I said that I'll take one data point and calculate the distances between that data point and all the other data points and use that to calculate the silhouette score. This is the silhouette score of this point. Right? I'll show you. We are still not done with calculating silhouette score for this data point. Like that, right? We'll take this data point and calculate this score. This data point and calculate this score. This data point and like that every data point. Here also this data point will calculate this data point. In all clusters, all data points will take and calculate this score and take an average of it. Right? Average score of all samples explain the separation distance between cluster. Right? The score, the numbers we'll see in a moment. Right? Silhouette analysis is there. We'll see that latter point. But as a whole, right? The distances are used to calculate this particular score for each data point. Okay, how is this calculated? Let's take S1, a sample from cluster C1, and is close to C2, C0. Okay, C1 is a cluster, C0 is another cluster. I have taken one data point S1 from cluster C1. Right? Maybe it's other C1 only. Green one is C1. Right? The cluster 1 and this data point is close to the C0. I have chosen a data point which is close to C0. This is for explanation purposes. Okay, AI, right? In this formula we have BI, AI, right? So what is AI? Sum of distance from S1 to samples within C1 cluster. Okay, A1 is equal to this data point to distances between all these data points within the cluster divided by number of data points within C1 cluster minus 1. Number of data points, how many? 1, 2, 3, 4, 5, 6. So 5. 5 is the denominator. So I have taken the distances, right? Distances between this data point and all the data points within C1, right? 20, 0, 26, right? 14.4, 20, 28 divided by number of data points within cluster C1 minus 1. Okay, that is A1. In this formula, This A1 is calculated like that. Okay, and B1 minimum of average of, right, there is a big thing here, minimum of average of distance from S1 to samples in C0, right, distance from S1 to samples in C0, distance from S1 to samples in C0 is what? S1 to samples in C0, average of all those, right, all these numbers average I calculated and kept here. Okay, average of distance from S1 to sample C2, right, if there is another cluster C2, right? If there is another cluster C2, I'll take average of that also, right, here I can take average here, right, I'll put it here, right, so from C2 also I'll do the same thing, from this data point to C2 I'll calculate and then take average and keep it aside like that. K number of clusters are there, I'll take averages of all those distances between this data point to all the data points in those clusters. Each cluster will have n number of data points, so we'll get n number of values here and then we need to take average of it. So all those averages I have taken and minimum I have taken in that. So what am I doing here? I am trying to calculate distance between this data point and the first cluster, this data point and second cluster, this data point and nth cluster, and taking the minimum of it. That means closest data point I am taking, closest cluster, right? The distance between this data point and the closest cluster is Bi. Did you get it? The distance between this data point and the closest cluster is Bi. AI is the distance, the the average distance. Basically, this is also average only. We are taking C1 cluster minus 1 because we are eliminating the data point in itself. See, this data point in itself is 0. You take average. You want to take average. If you should not be doing by 6, by 5 only. You should be doing. Do you agree with me? I am taking average distance of all the average of all the distances between the data point and other data points, right? So I should be taking number of data point minus 1 because distance between that and that itself is 0, right? This is also average only. AI is the average of the distances between the data point and the other data points within the cluster. Okay, the BI is the minimum distance between this data point and the other clusters, right? Other, closest cluster. Sorry, the distance between average distance between this data point and the closest cluster. Now I am calculating silhouette score. The closest cluster distance minus within the cluster divided by maximum of these two. If this comes negative, right? What that means? Closest cluster is overlapping. If it comes positive, right? The closest cluster is farther. That means this BI is going to be bigger than AI, right? The closest cluster is farther. That means this BI is going to be bigger than AI. That means it's going to be positive. And we are actually taking maximum here to normalize it. Now, when you take maximum here, the number is going to be between 0 and 1. Either it can be negative or positive, depending on BI and AI. Did you get it? The silhouette score is actually trying to look at the data point and the distances between the data point within the cluster and the data point and the closest cluster distance between the data point and the closest cluster, and whichever is high, right, depending on that you will get negative or positive. If the clusters are overlapping, you will get negative. If the clusters are not overlapping, you will get positive, and the number is going to be close to 1 if they are very far. If the number is going to be close to 0 if they are very close. It's going to be negative when they are overlapping. So silhouette score will clearly show you what is happening with the clusters. I'll take one example for each of these scenarios: overlapping, too far, too close, and try to explain. At a high level, did you guys understand what I'm explaining? Yes, no?
Yes, sir.
Yes. Yeah, a little bit confusion will be there because this is like that within cluster, between cluster, that whole confusion is going to be there. But once after finishing class, right, you go through the notes, you'll understand. If you have questions, right, tomorrow I'll answer that. Okay, so you need to work out. Okay, this I tried my level best to create examples here. There is no resource on the internet to show this clearly. Okay, so try to try to make use of it. So we'll try to see one example for each, right? Silhouette analysis, clusters from far from each other. Okay, individual sample scores close to 1, right? Farther sample score greater than closest sample score. I'll talk about this in a moment, right? Individual sample scores close to 1, right? Farthest sample score greater than closest sample score. This is going to be true, right? Here in this kind of scenario. So we have seen that, right? So I have taken this data point and calculated distances, took average, that is AI. I took this data point and calculated distance between all the the cluster things, and I took average of it. Why did I do by 5? Oh, there are 5 only. Okay, there are only 5 numbers, 5 data points there. So we have only one cluster, neighboring cluster. So minimum is going to be that one only. We have another cluster also. We would have calculated that also and took minimum, but it's going to be complex. Mathematically calculating manually, it's going to be complex. So I have taken only one neighboring cluster. I took AI, BI, substituted into it. I got for this data point, I got 0.776. Okay, far silhouette score for far clusters. Two clusters are too far, so I've got positive number and a number close to 1. Okay, silhouette score for farthest data point. See this here, this is a closest data point to the neighboring cluster. See this, we have got 0.776. I have taken a farthest data point from the neighboring cluster and tried to calculate. See this, it is more, right? This is 0.776, this is 0.825. Right? So silhouette score is clearly going to show you whether a data point is close to the neighboring cluster or far from the neighboring cluster or overlapping with the neighboring cluster. Okay, so that is another example, right? So closest to each other. So I have taken another clusters, two clusters which are close to each other. Okay, and tried to calculate a data point which is close to the neighboring cluster. See that 0.175. A data point which is far from the neighboring cluster, 0.593, right? See that? Okay, and again an overlapping cluster also I have taken. Overlapping clusters I have taken and I calculated the distances, and I did a data point which is very closest, right? Very closest in the sense deep into the other cluster, and calculate. See this negative score I have got minus 0.595. Okay, I'll take a farthest data point and try to see 0.18. So when you look at the closest one and farthest one, you can assume how exactly the other data points scores are going to be. When you take average of it, right, within the cluster, right, you will get the total score of the cluster. Okay, so that's how you calculate individual data points silhouette score, right? Once you have individual data points silhouette score, you take average silhouette score for all samples, explain the separation distance between clusters. Okay, all samples. You take all samples silhouette scores in all the clusters and take an average. That actually shows you, right? If all are coming like this, negative scores and positive scores, which are kind of close to 0 and negative. When you calculate average of all these data points silhouette scores, what will happen? Farthest, closest point is very negative, right? Farthest point is almost close to 0, right? You can assume the other numbers, right? Other numbers calculated here. If you take average of the total thing, right, what will happen? Is that number going to be close to 1, 0 or 1? guys? Is the data point close to, is that ultimate score going to be close to 0 or 1?
Close to
0.
0.
0, right? Or negative also. Sometimes, if it is too much overlapping, many of these data points, silhouette score will be negative, and some very, maybe these 3 points will get positive, but most probably it will get negative. That way, right? If the total average score is negative, that means all clusters are overlapping, right? If total, or that the total score is going to be positive, right? This way it is going to be positive, right? Closest data point itself is a little very close number to 1, and farthest one is going to be even closer, right? When you take average, right, that is going to be definitely close to 1. If they are like close to each other, right, the number is going to be close to 0. Okay, so that way total average silhouette score is the silhouette score for total clusters. That actually shows you whether the clusters are overlapping or far from each other. Okay, close to each other. So this way, right, rather than trying to calculate distances between, these uh, cluster centroids and the data points, now this way in a single number you will get to know, right? They are also single number, but here you'll get to know clearly what is happening, silhouette score. Okay, so this is a very important question in interviews. Many people will ask, even though they don't know, they don't really understand what exactly happening, they'll ask. But if you can understand it and explain it properly, right, that's going to be better. Okay, so once after doing all this, right, for each data point we calculate silhouette score, right? So we can do a plot like this. Silhouette analysis we call it as. Right? This is within one cluster. So suppose that there are 4 clusters. Okay, and we need to decide whether 4 clusters are good enough or not. Right. So there are 2 questions. Right. One is how many number of clusters should be there, and how the score should be. Right. Basically the major question is how many clusters is the best, because we don't have a y variable, we need to decide. So that can be decided using silhouette analysis. Okay, for each data point there is a silhouette score, right? So if they suppose that there are many data points in first cluster, there are many data points in second cluster, third cluster, fourth cluster, you try to take silhouette scores on x-axis. Okay, for each group you just try to do a plot. They are going to come like these knives. Even if you do, practically also, they'll come like this one. In scikit-learn library, they gave code to do this. So silhouette analysis, they gave the code here. You can actually copy paste it and use it. Okay. So here, right, what is it showing? The height of this thing is number of instances in the cluster. Right, height is nothing but um, in this particular cluster, all the data points silhouette scores are spread like that. Okay, and the width is going to be silhouette scores of individual, right? How many, right? There are 0.001, 0.002, 0.02. There are many data points getting the same score here. That's where it is coming as a thick knife. So now you take average, right? Average of all sample silhouette score. What is that? The total clustering silhouette score. This method gives you. Silhouette score is the method which gives you average of all individual silhouette scores, all individual data points of silhouette scores. If that is, if that is like, if you take that average, right, it is actually coming like this, right? Then you can take the 4 as the clusters. The 4 as the best cluster. But if it is coming like here somewhere, right, then you shouldn't be taking it. These cluster knives, right, should be within that average. Okay, got it? Equally got distributed. That's what, if this line comes somewhere here, right, that means clusters are equally got distributed. Okay, so this line should be close to the tips of the knife, not the into the this whatever. Okay, got it? Individual clusters silhouette scores. Now all silhouette score should be less than the total average silhouette score of the total clusters. Did you get it? Any questions?
So here the best number of clusters is 3 or 4?
4. There are 4 clusters. If you do 4 clusters, you will get 4 knives. You do 3 clusters, you will get 3 knives. If you get two clusters, you get 2 knives. This is just an example diagram. I took it from this thing. I didn't plot it for our data.
Yeah, I got that. But the horizontal, the vertical line is actually, passing similarly with the 3 knives, but for the blue knife,
Yeah,
it
is
is
actually,
inside.
yeah, maybe 3. We will not know that, until and unless you do 3 clusters and do this again, you will not know that. So you need to do 2 clusters, do this graph, 3, do this graph, 4, do this graph, like that. Alright. Got it, right?
Yes. Yep.
Yeah, so you go through the notes and try to experiment. You will know better. Okay, so give me 1 second. Give me 1 second. Here I am. So now, right, we have seen what is clustering and how to actually measure the metrics. Also, we have understood. But we'll see, right? Yesterday, on Friday, I have shown you how to do k-means clustering and then find out k using elbow curve. I showed you. Here, what we did, we took k from range of 2 to 10. That means 2 to 9. It will do, right? And we are building k-means, and then I initiated with the k-means plus plus. I did not explain this. K-means plus plus is an initialization technique. Okay? K-means is an algorithm, and k-means plus plus is an initialization technique. So when we were looking into this clustering, I said that randomly we'll pick cluster centroids, right? Instead of doing random pick, you choose one data point. No, k-means plus plus I am explaining. You choose one cluster centroid and choose the next cluster centroid which is very far from this data point, and choose another cluster centroid which is far from that data point and this data point. Right? That way it will actually choose. The k-means plus plus will choose first cluster centroid randomly, and then choose the next one which is far from the first one. Choose the next third one which is far from the first two. If you specified k is equal to 5, it will actually choose first one randomly, second one far from first one, third one far from first two, fourth one far from first three, fifth one far from all 4 currently chosen cluster centroids. That way the initialization is going to be intelligent and number of iterations to find out the best cluster will reduce. K-means plus plus is an initialization technique which reduces number of iterations in finding the best cluster. Okay, while finding the best cluster, it is actually looking into within cluster sum of squares, right? So that within cluster sum of squares will come to minimal with less number of iterations if we use k-means plus plus. That's an initialization process. Okay, and then said random state is equal to 42 and fitted and then predicted. In the prediction, we'll get number for each row. We'll get one number, right? Each row will be assigned to one cluster, one number, one color. Okay, And then I'm appending that inertia underscore, which is nothing but WCSS, and Shilote score also I calculate. To calculate Shilote score, I'm passing X and the predicted values. Right? The cluster centroids I am passing, because while calculating Shilote score, it need to know which row belongs to which cluster, which row belongs to which cluster, right? So here, if you look at Shilote score, which row belongs to which cluster, it knows, then only it will be able to calculate these scores, right? So to calculate Shilote score, you need to pass your X train, right? The data, the input data, and then the predicted values are the cluster numbers. Okay, which cluster the each record belongs to. Now I appended the Shilote scores also, and now I am doing a plot here. See this, right? On the number of clusters, right? Cluster size 2, 3, 4, 5, right? Nine iterations we did, and then Shilote score is actually less in when it is 6. Okay, but at 3, right? We can actually do 6 also. I did 3. I don't know why. Maybe I did 3 and tried to do something and it did not work. No. Yeah, that's the point. See here, we know the data. We know that data belongs to 3 groups. Do you agree? The IRA data, it's iris data, belongs to 3 groups, right? Right? Do you agree? Species, how many species are there in this data? Iris data?
Yes, 3 flowers.
3, right? In general, when you are doing clustering, you don't know the Y variable. Okay, but in this particular case, I have taken it intentionally because I wanted to show that these metrics are not reliable. That's where you always need to use a supervised learning algorithm to measure whether the clustering happened properly or not. Okay, so
How did you say it's three, sir?
uh,
I
give,
didn't understand.
give me one second. Give me one second. We need to give me one second. I did not complete the statement. So here, in this particular data set, we know that data belongs to 3 groups, right? 3 groups.
I didn't
What,
understand that, sir.
what is the Y variable? In the Y variable, we have 3 different species, right? Satosa, Virginica, and versicolor, right?
I'm seeing say in the under the species column, I'm seeing
Huh.
the same name.
Same name, but you in our SVM class, right? I showed you how many different classes are there in this particular data set.
Okay, you are referring to somewhere else also.
No. You are not you are not practicing at all. Let me show you. So on in our SVM class, right? I showed you that how many different different classes are there in this, right? So dot see that 50 records belonging to Satosa, 50 belong to Virginica, 50 belong to versicolor, right?
Right.
Right. So this is the data set. I intentionally took this data set and tried to apply clustering to show you that unsupervised learning algorithms are unreliable.
Okay.
That's where on the day I started explaining the clustering, I told you that you will apply clustering as a beginning process, and then you have to provide a mechanism for the user to update the labels, correct the labels. Once the label correction happened, you may, at one point in time, maybe in 6 months or 1 year, you will get picture perfect data. Then you will be able to build a supervised learning algorithm. When you don't have labels, you should use clustering as the beginning process and try to come up with some kind of grouping, right? Maybe 3, maybe 5, right? Some kind of grouping. Use that grouping and try to provide user an interface where he or she will be able to update the data, update the labels. Okay. So this is the reason. So I have taken a supervised data set where 3 groups are there. When I tried to do clustering, when I looked at elbow curve, it actually is clearly showing that beyond 3 clusters it is not good, right? But when I looked at silhouette score, right, it is showing 6 as the best cluster. Data patterns may be different, but originally your data has got only 3 groups. So if you took silhouette score as the basis and tried to do 6 groups, you have to provide user an interface where user will be updating it to correct the mistakes done by the clustering algorithm. Maybe in 6 months you will actually cumulatively collect the data, make the users update, then use that data to build your model, build your final clustering model. So sorry, build your final classification model. Got it? The metrics are not reliable. Theoretically, they may sound very exciting. You see this? It sounds very exciting when you look at it theoretically. But elbow curve is working here, silhouette score is not working. In some other data set, right? Elbow curve will not work. Silhouette score will work. In other data set, both may not work. When I say may not work, the reality is different. There are 3 groups only. But when you looked at elbow curve, it is saying 3 groups is the best. But when you look at silhouette score, it is saying 6 groups is the best. Which one to believe? If you don't have the y variable, do you have a clue on which one to believe? Do you have a clue on which one to believe? If you don't have y variable, do you have a clue on which one to believe and choose the best k? Are you getting it?
So when you say y variable, the number of values in the y variable, that 3 categories, that's what you are referring to.
Yeah. Generally when we do clustering, when there is no y variable available, we try to do clustering, right? And try to find out the groups in the data and try to do some, it is like classification, blind classification, right? Clustering is nothing but blind classification. Do you agree?
Yes.
Right? You're blindfolded and you have given 3 sets of fruits and you need to touch them and say what it is. Sometimes we may go wrong, right? If there are apples and custard apple, right, you may not be able to distinguish between both when you're blindfolded. But as an initial step, we will ask you to do that, right? And then we'll introduce we'll unfold you and then try to make, or maybe we'll bring a blind person, right? Then there is no classification available, classified data available or labeled data available. We will use clustering. If I have to explain that in real world, suppose that there are many people who are blindfolded and there is only maybe few people who are not blindfolded, and we need to use those blindfolded people to do classification. What we will do, we'll give them and ask them to do whatever they can, and the people, less people who are actually there, who are not blindfolded, we'll ask them to correct it at one point in time, right? Maybe cumulatively at one point in time you will get all the data corrected or the labeled. Then you can use that data to build a classification model. Got it? I'm actually explaining a real-time scenario when there is no labels, how clustering can be used. I'm trying to explain. Did you get that point? Yes, no? No?
Yes.
Okay. Yeah. So many clients doesn't know this particular thing. Many data scientists also doesn't know this particular thing. Right? They'll try to do false promises to the client saying that we can do, right? Clustering or dimensionality reduction, or in general the unsupervised learning algorithms are not fully capable, fully mature. You should never rely on unsupervised learning techniques and promise something that you can deliver. You can use this as a building block for the total, ultimate project, but you cannot use that as the ultimate thing. So that is the example here. I took a supervised data set to show you that the problems with the elbow curves based on the WCSS, within cluster sum of squares, and the Shillot scores. Sometimes this works, sometimes this works. You don't know. Sometimes both may not work. Right? So it's a best approximation of K, and we have taken K is equal to 3 because we already know. See the outcome, the cluster's outcome. The prediction is going to be number for each cluster. Okay, you can actually visualize, right? So in this data set, I have 4 columns. Okay, I can do clustering. When I did clustering, for each row I have got one number assigned, or the cluster number assigned. Okay, and then I am reducing the dimensionality to 2 dimensions. The 4 columns I am reducing it to 2. Then I am combining, right, the reduced dimensionality 2 columns data and the clusters, and trying to do a plot to see how the clustering happened. All these data points belonging to, so these two are close to each other. This cluster is far, but here they are not in circular shape, right? This is just to give you a high level understanding on how the grouping happened. Okay, so you can visualize the clusters also by reducing the dimensionality. Okay, this is another use. You have a huge data, you did clustering, you know if the data has got y variable, right, you can actually do the dimensionality reduction to 2 dimensions and do a plot, but that is not good practice because you lose lots of essence from the data. Because we have 100 columns and reduced to 2 columns, you will lose a lot of data, lot of essence in the data. Visualization is not going to be useful. But many people try to do this and show that that as they were able to produce a 2-dimensional graph out of 100-dimensional data. But this is not a good approach. Okay, got it? Got it? How what I did here? Did you get it? I take it as yes. Now what I did is I took our handwritten digits data, right, and then tried to find the best k. Right, when I tried to find best k using Shillot score, and I actually printed Shillot score here, right, and then when I tried to do WCSS, right, see this here. Is there an elbow? Do you know where exactly the cluster? Do you know how to choose the cluster k, size k, by looking at this graph?
No.
Also.
No, right? This is another problem with elbow curve. It will not always give you the clear, clear cut where maybe here, maybe somewhere here we can actually choose maybe 8 or so, right? But it will not give clear cut there. Okay, I took a Shillot score and tried to do a plot. See this here? It's actually jumping around. Right? I chose k is equal to 8 because here I am pretending that I don't know the y variable, right? In this digit recognized data, I have 10 groups, right? I know 10 clusters are there. Clusters and the on a classification data set, the number of classes is same, right? So I have taken 8. I am pretending and I have taken 8 and tried to do the clustering and try to visualize it and show. See that? Reduced that 784 dimensions to 2 dimensions and then try to do the plot. This is not right. This is definitely not right. But some people did it. I'm actually trying to show you the technique. So can we use the clustered data to improve the model accuracy or not? On a classification data set, right? You can take this cluster number as another column. Do you agree? For each row, there is going to be one number, right? So there are 784 pixels. I'm going to add 785 fifth column as the cluster number. after doing clustering. And then try to do the supervised, no, whatever. Let's see this here. I appended this cluster thing to the X-train, then did fit transform, right? Standard scaling, then build a model. See, it did not improve much, but some cases, right? When the classification algorithm is not working well, you can actually take the clustering as a help, right? You do clustering and add that as a new column to the data set and then build a model. And then it may improve a little bit of performance. Okay, on a supervised data set, when the model is not working well, you do clustering, add that cluster column as the new column to the data set, and then build a model which may improve your accuracy. That's another help from this clustering algorithm. Okay, got it? Any questions? So I'm going to stop it here, and tomorrow I will explain DB scan.